There's a story about the Greek mathematician Hypasus that's well known, albeit likely to be apocryphal. Hypasus was a Pythagorean, a communal religion based on the teachings of Pythagoras. The central belief of the Pythagoreans is that all is number. By that they mean that the true nature of reality is exposed in mathematics, which for them was the relation of counting numbers. Music, for example, was the result of ratios. Strings plucked at random places generate cacophonous noise, but strings whose lengths were simple ratios of small numbers generated wonderful harmonies. We have mathematics connected to a physical system generating experienced human beauty. It's in this way that the notion of ratio gave rise to the notion of rational. That which is reasonable to believe, that which is in line with the universe, is expressible in terms of ratios of numbers. Now, perhaps the most famous result of the Pythagoreans is the Pythagorean theorem, which says that for a right triangle, the sum of the squares of the lengths of the sides equals the square of the length of the hypotenuse. Now, what Hypasus did was consider the simplest of these triangles, one with a side length of 1, and thereby a hypotenuse of the square root of 2. And he then proved with absolute certainty that the square root of 2 cannot be expressed as the ratio of two counting numbers. The Pythagoreans' most famous result contradicted their most deeply held and cherished belief. The mathematical order that Pythagoreans believed defined reality undermined the very order they thought it created. The story is that when Hypasus told them of the discovery, they threw him off a ship and left him to drown. The interesting thing about history is how it repeats itself. In the 20th century, chaos theory, also called complexity theory or systems theory, developed out of the mathematical structures that scientists thought provided a picture of an elegant universe. But the mathematical structures that they thought provided this simple and coherent picture went on to reveal a reality that was actually much more complex and messy. The more things change, the more they stay the same. Now, fortunately, these days no one gets thrown off of ships for such work. You're just denied tenure. But the shock and resulting rethinking of reality is just as striking. When we talked about quantum mechanics, we saw that what bothered Albert Einstein the most was the inherent randomness in the theory. The result of Schrödinger's equation for physical systems was a wave function. Right? That is a mathematical combination of every possible state the system could occupy. Again, we never see anything in the superposed state, but only in a particular state. The quantum system develops as Schrödinger says it should, but the instant we observe it, it goes from the superposed state into one and only one of the property states, and we're powerless to predict which one it will be, no matter how much we know about the system. It was this powerlessness to determine the future from the past, based on a complete scientific theory, that so upset Einstein and led him to his famous dictum, God does not play dice with the universe. Randomness has no place in a universe which should be deterministic and predictable. Now, dice, interestingly, play a significant role in our understanding of probability and its relation to the universe. In 1654, a French nobleman, the Chevalier de Marais, contacted the famous French philosopher and mathematician Blaise Pascal about a gambling question. Pascal got in touch with his friend and colleague, the great mathematician Pierre de Fermat, and asked him. The Chevalier de Marais was playing a game in which a pair of dice would be rolled 24 times, and players bet on whether double sixes would be thrown or not. He realized that he won more often when he bet against, but only slightly more often. He played a lot and so had a sizable sample. He wanted to know if this sense was correct. Fermat answered by creating the mathematical theory of probability. A century and a half later, Pierre-Simon Laplace, one of the greatest geniuses of the 19th century, often called the French Newton, became interested in extending Fermat's notion of probability beyond games of chance to show how it functions in science. So, amidst all his other great advances in physics, he wrote a pair of books on the subject. Laplace's first book, An Analytic Theory of Probability, showed how to use statistical methods to solve problems in science. Early on, he says, "This theory of probability is one of the most curious and useful things I have ever worked on." But while he found it useful, it wasn't deep. 2 years later, he wrote another book called A Philosophical Essay on Probabilities, where he argued that the use of probabilities in science is the result of our own lack of knowledge, not the result of a world that is in any way random. The most famous passage from the book is this one, in which Laplace writes, "We may regard the present state of the universe as the effect of its past and the cause of its future. An intellect which, at a certain moment, would know all the forces that set nature in motion and all positions of all items of which nature is composed, if this intellect were also vast enough to submit these data to analysis, it would embrace in a single formula the movements of the greatest bodies of the universe and those of the tiniest atom. For such an intellect, nothing would be uncertain, and the future, just like the past, would be present before its eyes." This intellect has been called Laplace's demon. The idea is, consider a being with superintelligence, capable of remembering an infinite amount of facts and who could compute with infinite quickness. Now, give this superbrain demon two things. First, the true laws of nature. Laplace assumed these were Newton's laws with which he made major advances. And two, complete information about all the masses and energy in the universe at any one moment. Given these two things, the demon could then predict with absolute certainty the state of the universe at any time in the future and deduce the same exact state of the universe for any time in the past. The universe, Laplace claimed, would be completely transparent to this mega intellect. Laplace's demon is the ultimate statement of the Enlightenment project embodied in science. Science's true aim, according to this line taken up by Laplace, Einstein, and many others, is to develop a unified account that's capable of predicting and explaining every event, every occurrence, everywhere. This true aim of science makes four basic assumptions about science and the universe it's trying to describe. First is that it's deterministic. This means that the state of the universe and every part of it at any given time is completely determined by the state of the universe immediately before. If a system is in state A, then it will transition to state B. B always and necessarily follows A. The second, related assumption is that the rules by which we can derive state B from state A admit of what we call steady state solutions. That means we'll see recurring patterns of states. Planets orbit in closed paths over and over again. The future is not only determined by the past, but determined in ways that are simple, elegant, and clean. Now, I once asked a friend of mine who's a mathematician whether math is a science, and if so, what is it the science of? Without missing a beat, he said, the science of patterns. The reason scientists use equations to describe the behavior of physical systems is because the mathematical language, the language of patterns, is presumed to apply to the behavior of the world. One of the most striking examples of the two assumptions, though, is non-mathematical. It's found in the writings of the 19th century German philosopher Friedrich Nietzsche, who in his books The Gay Science and Thus Spoke Zarathustra considers the doctrine of the eternal recurrence. So, if the universe is nothing but atoms bouncing around, and the bouncing of those atoms is governed by Newton's quite deterministic laws, then they will bounce in a way where the future arrangement is completely determined by the past arrangement. But in the same way that monkeys banging on a typewriter will eventually produce the works of Shakespeare, atoms bouncing around will eventually return to an earlier configuration. But if this is true, and the arrangement at any time completely determines the state to follow, the only thing that could happen is everything that has already happened. History, Nietzsche contends, would be compelled to repeat itself over and over again. Everything we do, we've done an infinite number of times in the past, and will continue to do an infinite number of times in the future. This may give each action a sense of importance in its permanence, or a sense of dread, as expressed by Woody Allen's character Mickey in his film Hannah and Her Sisters. When Mickey's considering Nietzsche's idea of the eternal recurrence, he remarks, "Great, now I'll have to sit through the ice capades again." So, we have two assumptions. Determinism, that the present state determines the future state of a physical system, and steady state solutions, that the development of the states over time is well behaved and follows a simple pattern. A third assumption inherent in Laplace's Enlightenment view is the stability of those steady state solutions, that a small difference in makes only a small difference out. The fourth is predictability, that since things develop as they have to, according to the rules, in a simple, orderly way, if we have the rules and the data, we can predict what is to come. Quantum mechanics has thrown doubt on the deterministic and predictability aspects. But recent work on chaos theory has led us to believe that even if there are aspects that are deterministic, this does not necessarily mean that the results are steady-state solutions, which are even stable and predictable, even without the sort of randomness that seems to be part of observing quantum systems. Laplace's view seems overly simplistic, almost naive. The assumption Laplace was making is that if we have deterministic laws, that is, laws where what we plug in uniquely and completely determines what we get out, then we can use those laws to always predict what will happen if we have the requisite data to plug in. Chaos theory says, hold on a minute. Just because the world may have deterministic rules governing the motion of particles in it does not mean that we can necessarily predict their motion from those theories. The most famous problem here is what's known as the three-body problem. Newton became the most famous man in the world when his theory of motion and his theory of gravitation were combined to explain the elliptical orbits of the planets as shown by Kepler. Kepler crunched the numbers, came up with the shape, right, an ellipse, right, with the sun at one focus, but no one knew why the planets moved elliptically. Newton gave us his three mechanical laws and his law which said that the attraction between any two masses is inversely proportional to the square of the distance between the objects. Applying these two rules to bodies in space, we ask the question, how do these bodies interact? That is, how does the gravitational attraction between them make them move? And we set up the equation, plug in the initial conditions, and there's a simple solution. The bodies move around each other in such a way that if one were thought to be nailed down, the other would move around it in an ellipse. Outstanding. But we don't live in a universe with only two things. Suppose we enlarge our scope to look not just at the Earth and the Sun, but at the Earth, the Sun, and the Moon. We have the Moon going around the Earth and the Earth going around the Sun. The Moon's pull on the Earth is tiny compared to the Sun's because the Sun is so much bigger. As a result, the Earth's orbit will not be perfectly elliptical, but perturbed in some way. The problem is that when we use Newton's laws the way we did for the two-body case, the equations are no longer solvable. There's not a class of steady-state solutions, repeating trajectories like an ellipse with the sun at one focus, which is the general solution to the equations. In certain very simple artificial cases, like say three identical perfectly spherical masses all moving around in a perfect circle together, right? In those cases, we can come up with a simple steady-state solution. But for anything resembling the messy, complicated real world, the equations have no exact steady-state solutions. There is no way in our mathematical language to set out a description of the path in space. Our mathematical language is a language of patterns, but the patterns just aren't there. Now, the important word here is exact. We don't have an exact solution, but using simplifications, assumptions, and ignoring certain elements, we can come up with approximations. Now, especially now with the use of powerful computers, we can, for a number of cases, come up with a general idea of what the path of three bodies would be, given a certain set of initial conditions. These approximations are extremely useful and quite good. But while we can get most of the way there, there's much that's interesting in the gap between the approximate and the real solution. It's in that gap where you find chaos theory. These cases are complex, where complexity is a technical term denoting an important aspect of the equations we take to govern the system. Scientists love when the state equations for a system are what we call linear. A linear equation can be graphed so that its solutions form a line. Now, a nice property of linear equations is that they're stable. A small change in the initial conditions leads to a correspondingly small change in the outcome. Consider my morning commute. Right? There are 2 schools in my area, and I have to drop my son off at the one he attends on my way into the office. Now, if we leave the house at 7:31, it takes 12 minutes to get him to the front door of his school, and we arrive at school at 7:43. If we leave the house at 7:32, it takes 12 minutes, and we arrive at the front door of the school at 7:44. But if we leave at 7:33, I make my third turn and see the back of a big yellow school bus going to the other school. It stops. A mom waves frantically out the front door. After a few minutes, a couple of kids leave the house, saunter to the bus, walk up the steps, walk to a seat. Eventually, they sit down. The bus driver turns around and shouts something. Finally, the red lights stop flashing on the sign on the side of the bus, and it moves forward 50 feet. When it stops at the next house, and the whole process begins again until my son arrives 10 minutes late for school. This is an unstable system because a small difference in initial conditions when we leave the house results in a significant difference in the result when we get to school. This sensitivity to initial conditions is the hallmark of nonlinear equations. The commonly used phrase to describe this is the butterfly effect, and comes from the Ray Bradbury short story, A Sound of Thunder. In the story, a time machine has been invented, and people are transported into the past to hunt dinosaurs. Now, the guides are well aware that the future is contingent on the past in untold ways, so they've constructed a levitating walkway that everyone must stay on, and they only hunt dinosaurs that were about to die anyway. Afterward, they remove all bullets, all other traces, leaving the past undisturbed. During this hunting expedition, to bag a Tyrannosaurus, which was going to be crushed by a falling tree, the hunting party discusses with relief the recent election in which a Hitler-like candidate lost narrowly to a more sensible candidate. Just then, they find the T-Rex, and the customer who came to shoot it is so frightened that he falls off the path. The guides do everything they can to minimize the effects of the event, but they return back to their original time and find that the evil candidate has in fact won the election. Looking at the customer, they find a crushed butterfly on his boot. The life of that butterfly had effects that we didn't realize, and without it, everything changed. The way we normally phrase it now eliminates the time machine and substitutes something more mundane, the weather. Edward Lorenz, the father of chaos theory, entitled his most famous paper, Does the Flap of a Butterfly's Wing in Brazil Set Off a Tornado in Texas? Now, Lorenz was a meteorologist at MIT in the 1960s, where he used one of the first big computers to create the first computer models of the weather. Now, by current standards, it was an extremely simple model, but for the time it was incredible, and the results actually looked like developing weather systems. Now, one day, in the middle of a run, Lorenz decided to stop the model and restart it when he came back to the office a few minutes later. He wrote down the values for all the variables, turned off the machine, and then when he came back, restarted the run where he had left off. Or so he had thought. An incredible thing happened. The weather in the model that developed was completely different from what was happening when Lorenz stopped the machine. He was puzzled. Could it be an error? Then he realized that he had taken the values of the variables, which the computer computed to 6 decimal places, and had only written down the first 3 digits of each. Surely the numbers in the tens of thousandths, hundreds of thousandths, and the millionths column were not that important. But he tested it, and they were. Small differences in didn't lead to small differences out. Incredibly subtle changes in the value of the input into the model yielded massive changes in the weather as it developed. In the first computerized model of the weather, a butterfly's flap in Brazil could generate a tornado in Texas. Such sensitivity to initial conditions is a problem because no matter how sensitive your measurements, the act of collecting data itself comes with what scientists call experimental error. Now, by the word error here, they don't mean mistakes. Rather, that there's always a resolution attached to any instrument. It can be incredibly sensitive, but the level of sensitivity is always finite. There's a limit to how precisely we can measure something. But if the limit's sensitivity to initial conditions is sufficiently small, it will far fall below our ability to distinguish between relevantly different states of the system. The development will appear random and become unpredictable, even though it's thoroughly deterministic. Systems like the weather are physical systems. They must obey the laws of physics, and in that sense have to be deterministic. But they are sensitive to small changes in initial conditions and are unstable. That is, they do not have simple repeating behaviors. Governed by nonlinear equations, systems like the weather, or on a smaller scale, the smoke coming off the end of a cigarette or cream mixing into a coffee, are incredibly complicated. Physicists like order. Their job is to look at intricate systems and find ways to represent them as simply as possible with equations. Small deviations from the large-scale order are dismissed as noise. Only the large-scale regularities are given attention. Right? Remember the joke from an earlier conversation about the farmer who hires the physicist to design the chicken coop, who begins by assuming spherical chickens? Chaos theory demands that scientists think differently, that they pay attention to the actual shape of the chicken. That is, that they heed these micro deviations that they prefer to ignore in order to find the large-scale regularities. When they started to focus on them, something fascinating revealed itself. The behavior of chaotic systems was non-repeating. When we have a periodic system, prediction is easy. If Halley's Comet comes around every 76 years and it was last seen 75 years ago, get ready. But when a system is chaotic, there are no steady state solutions, no periodicity, and seemingly no predictability. But it's not random. And when scientists began charting the development of chaotic systems, large-scale regularities did begin to appear in the results. Unlike Nietzsche's recurring historical loop, the evolution of these physical systems over time would not return to the same state. But when the states were mapped on a mathematical structure called phase space, patterns began to appear. If the chaotic systems were truly random, then the system's path through phase space would be like that of a drunk wandering down a street. You never know where he may weave or stagger next. There's no place to stand, right, without the risk of being bumped into by this inebriated fellow. This means that there is no state which the system might not occupy, and the sequence of states which the system could be found in could lead to any other state. But when we plot out the development of the chaotic system, there isn't the simple map we see in predictable stable systems, yet there's also not the random craziness either. The line that is the representation of the system's time evolution could be complicated in odd ways, but it will take definite forms. It might be a torus, a donut shape. It might look like the wings of a butterfly. It might resemble a saddle. The path of the system represented in phase space will stay on these surfaces and eventually fill them in. Mathematicians call these surfaces strange attractors, and the mathematical structures of their surfaces are the most popular element in chaos theory, fractals. A fractal is a shape that's self-similar when you look at different scales. Right? If you look at a fractal pattern and zoom in on any segment, that segment will look like the larger section you started with. We can think of one of the simplest fractal patterns, the Cook curve, also called the Cook snowflake, named for its originator, the Swedish mathematician Helge von Cook. Start with an equilateral triangle. That is a triangle with 3 equal sides. Now, take each side and use the middle third as a side for another equilateral triangle. This means that each of the 3 sides of the triangle now has a triangle sticking out, right? The shape is the familiar Star of David. But now, take the 2 outer edges of each of those 6 triangles and use the middle third of them as the edge of yet another equilateral triangle. Now, it looks like a snowflake. You can take all of these little triangles and again build more triangles off of them again and again and again, infinitely many times. The result is the Cook snowflake. It's a strange shape, right? When we went from the original triangle to the Star of David, we increased the perimeter of the shape. It's a longer path around the Star of David than around the original equilateral triangle. And for each iteration, each addition of new triangles, the length of the perimeter of the snowflake grew a finite amount. Since we did this an infinite number of times, each increasing the length of the perimeter a finite amount, the result is that the length of the perimeter is infinite. However, and this is one of the weird things, the area inside is finite. We have an infinite line closing on itself, enclosing a finite region. If I had a circle of infinite circumference, I would have an infinite area inside. But the Cook snowflake has an infinite perimeter with a finite interior area. But the interesting aspect for us is that because of the way it's constructed, any place you look at the Cook snowflake, no matter how close or how far you are from it, still looks the same. This self-similarity across different scales is the hallmark of fractals. We find this sort of geometry in all sorts of irregular but not random places in nature. Leaves on trees, cracks in the earth, coastlines, the internal structures of crystals. Since we find fractals in nature, we also use them to model nature. Not just scientific models like those we use to predict the weather, but also in art. Since 1982, artists have been using fractals to create more realistic landscapes in the computer-generated graphics for backgrounds of movies. The masters at Pixar developed the technique for Star Trek II, The Wrath of Khan. In the animated sequence that introduces the central plot device of the film, the Genesis effect, which makes uninhabitable planets into lush areas suitable for life, the transforming planets are made real by the first use of fractal drawing in film. It's since become a standard tool in the graphical design toolbox. Reality seems more real to us when it's modeled on chaos. Science seeks order in nature and finds it. But that order is so complex that it seems to give rise to disorder. But in examining that disorder in a closer way, we find a new order. Chaos is not randomness, but a complexity within the universe we never thought was there. Our attempts to make the world comprehensible at first led us to demand that it be regular, simple, periodic, predictable. Nature said no, and we had to change our image of it. But it does not mean that science is useless. To the contrary, it's science that gave us this richer sense.